Okay, I literally tried plugging in a USB into an HDMI port to record this video. I don't know why. Alright, so today's going to be a relatively short video. I'm going to be talking about the Fibonacci sequence and how you can find the nth term in O of logN time, runtime complexity. So let's begin, shall we? So what's the standard way of finding the nth term? Well, just write out all of the nth terms. By default, you start off with 2 1s followed by literally everything else, which is just the previous 2 terms added together. So 2, 3, 5, and of course you probably already noticed, so I'm not gonna write out everything. This thing here, where you take the sum of the previous 2 terms to get the next term, well, that could just be written as the recursive formula an equals an minus 1 plus an minus 2. And my computer is really slow right now, so it doesn't seem like I can write anything. But you're just going to have to bear with me here. So we just have this formula, and we have, of course, the 2 base cases, A0 and A1. But this doesn't exactly help because you're just putting what you already know in your head into math terms. So if you want to find the nth term, you still have to go through A1, A2, A3, A4, and so on and so forth. But what if you didn't have to do all of the intermediate terms? What if you just had to know what the first 2 terms were, and you can find any term in the sequence? Well, let me introduce something called a state. And what a state is, it's basically just some abstract notion where if you know a state of the sequence, you basically know the entire sequence. And what state am I going to use here? Well, just 2 elements. Well, any 2 consecutive elements will work for the state, but since we know the first 2, I'll just say our state is A0, A1. And I'm just going to write it as a matrix like this because it looks cool. So our state here can be 1, 1, but it can also be any 2 consecutive terms. So the next state here would be 1, 2, and the one after that would be 2, 3. And of course, from any of these states, you could just jump forwards or backwards to get all of the other numbers. So, why did I put them like this? Well, do we know how to jump from one state to the next state? Well, yes, of course we do. It's just the formula. But now, instead of 1 term, we have 2 terms. So, let's say we wanted to jump from A0, A1 to A1, A2. Well, A2, I'm just going to write it as A0 plus A1, just to keep everything consistent. Now, in order to get from this to this, we need to multiply it by something. Since originally I wrote the state as a matrix, so if we multiply this by a 2 by 2 matrix, we can get a 2 by 1 matrix. And so in order to get A1 here, we need to do 0 times A0 plus 1 times A1. And to get the bottom one, it's just 1 of each. So, essentially, we can generalize this to going from one state to the next state for everything. But what we have here is just the transformation matrix to get from one state to the next. So that means if we wanted to go to the state after that, we just multiply by another one of these matrices. And if you want to get to the nth state, well, you can see where I'm going with this. You just replace this exponent here with n. And once you evaluate this, you just multiply by the starting state, and that's your answer. Well, obviously you have to take the bottom term here, because Actually, no, you want to take the top one because the nth term here, like the first term here, the top one is the first term of the sequence. So therefore, for the nth term, you want to find the top of the nth state here. So let me just write this a bit better. If we want to get the nth term, we just multiply our starting state by our transformation matrix. 0, 1, 1, 1. But now you might be wondering, if you're just multiplying this matrix n times, isn't that still O of n? And you didn't really change anything because you're doing like the same thing as before. Well, you're right. But that's where you have to do another optimization. And that is fast exponentiation. And if you don't know what that is, it's basically where you take like a power and you split it into a bunch of powers, into a bunch of descending powers of 2, such that the powers add up to n. And of course, you can always get a sum of powers of 2 equal to any number, because sum of the powers, well, the powers themselves, it's just the binary representation of the value, and you can represent any number in binary, so it works. Descending powers of 2, didn't we talk about that before? Yeah, we did, in our binary jumping video. So you can go ahead and watch that if you want. But anyways, once you do this with a variation of binary jumping, or just splitting it in half and doing it over and over again, you can calculate this part in O of log n, and then just multiply it by the original state to get your answer. So that's it for today. Thank you for watching, and we'll see you for COVID log or covlog number 4.